We're going to use Google Jules today. Google Jules has been around. I saw when I was getting set up with Google Jules. Hey, Ashford, hey, good to see you. We're using Google Jules today. Check this out. Google Jules, I had no idea, has been around for more than 2 years already. Isn't that crazy? This is a coding agent, something that, Codex and OpenAI, they're like, look, we came out with this really cool new thing, this new technology, this Codex that lets you run essentially Codex or Claude, like a CLI, a coding agent CLI. What's up? Hey, we're just gonna hang out today. We're gonna use Jules for the first time. This is gonna be. I've never used it. I have used Codex, which surprisingly just came out. Not Owen. Hey, how's it going? Jules looks pretty cool. I'm not sure what it does that makes it notably more asynchronous. Yeah, it's because it says it right here. It's like an asynchronous coding agent here at the top of the screen. You can see it's right there. It says asynchronous coding agent. We're like, all right, let's see. I don't know what makes it any more. I think the idea is it basically runs everything in a container in the cloud for you. That's kind of the idea. It's something like Claude Code. It's exactly like Claude Code, but you only use a web browser. So it's purely web browser, and then you interact through it, and you save data over into like a GitHub repository. Like as you can see here, we've got a GitHub repository set up, and I gave Jules access to it. Yeah, so that's the plan for today. We're going to try it out. I've never done it before. And what's crazy is Jules has been around for 2 years. And that is just mind-boggling to me that Google has been that far ahead of the game. And yet we're like, oh, hey, Claude Code came out. Let's just try that. But I'm just surprised at Jules. So we're going to actually get started. It gives you this interface. So basically, you sign up, you click the buttons. It sends you through an OAuth style workflow to connect to your GitHub repositories when you use Google Jules. And it says Jules tackles bugs and small feature requests and other software tasks. Direct export to GitHub. So you basically interact directly with all your files on GitHub. And then Jules does the work. It spins up a container in the cloud. It processes its own agent. And then it goes from there. So you can ask Jules to write anything. So we've got an empty repository right now. So what we're going to have it do is write a simple Rust machine learning, let's say deep machine learning framework, and show a simple. The hello world for ML training, AI training, I like is the XOR and XOR. Training example. The framework should have stochastic gradient descent for training phase, and let's see what else. I probably several activations phase, and then let's do like 10. Let's see, various activations. Like what are we doing today? Today we are using Google Jules, and we're gonna have it. We're gonna put it through the paces. We're gonna say, hey, we're gonna give you a very hard task. We're going to have it write a simple Rust machine learning framework using our instructions, and then we're gonna review it, and that'll be today's plan. It probably is not going to do probably won't build it like I would build it, but I'm very curious to see what it's going to do, how it's going to build it. Because we need to do back propagation with the gradients, and when we train it, we want to do it stochastically, and then we also want an XOR example. That's my favorite hello world example with training on AI models. When you're setting up your own framework, or if you're just getting started with, say, PyTorch or TensorFlow and Keras, for example, you would want the XOR example. Often you have the MNIST. Right, the MNIST training set, and that is usually the hello world for most of them. And it basically is a set of, it says 60,000, thank you for the likes, appreciate it. It's basically a set of 60,000 hand-drawn letters, or I guess in this case, numbers. And then you can use an AI model to sort of view it, and you can use all sorts of different models, like a CNN or vision transformer model, or just a basic deep learning model with a simple input. and no attention. You could do all sorts of things, and you can make a pretty good model from this data set using any kind of AI architecture that you're looking for. And it's small enough to run on a CPU, for example. So that's why it's usually the hello world for most cases. But I like even simpler. I like to keep things simple. So I like to use XOR, for example, the XOR training, because XOR is when you compare two Booleans, the outputs aren't a linear in comparison. So you can't use in order to train a model to understand the XOR operator, it has to be more of a deep learning. It can't just be a linear regression because it won't work. It just won't work. So that's why I like the XOR. That's a cool idea. Yeah, I'm excited because then Rust is going to be fast from a compute perspective on a CPU only. And then we can take it a step further. And after this is written, and then I want to rewrite it myself using my own design, and then make it really nice, because you can do operator overloads in Rust. So you can do like matrix multiplications. So you could have a simple A times B type output or input. Like you can use this syntax, and it will automatically do the matmul for you. And I like that. So we can create like our own layer-based framework. The inputs and outputs will match on the different layers. And so we can do a whole bunch of things to make it really nice. So we can do like a simple machine learning framework in Rust, because I've done neural networks and deep learning frameworks in Python and in JavaScript, and I want to do it in Rust now. So but before we do it ourselves, we're going to have the AI give it a chance, because I really wanted to check out Jules. Yeah, I wanted to see what Jules looks like. And so we're gonna try that. So we're writing a prompt. Look on the screen here, we got a prompt. Write a simple Rust deep learning machine learning framework and show an XOR training example. If you're familiar with it, then you kind of understand what the output should be, but you don't know. The problem is it can be any kind of, it's hard to tell because you don't know what the output's supposed to look like. And then you don't even know if it's like an efficient model, because you can waste a whole bunch of compute, and then your hyperparameters could be like really, really off by a lot. And so you're wasting a lot of compute on this training, and then you might get stuck in a local minima, or you won't find a global minima, because you can have the AI rewrite it. The AI gets better. You can have it rewrite it again, and it's like 17 cents. It's super cheap. So here we go. We're going to have Jules. We're going to give it a try. We've never used Jules before, so we're going to see how good it does. I'm not sure if it can do that, if it can do these things, but we'll find out. We'll see. The end result should be a simple to use framework in Rust, and showing an example with XOR training and inference. And inference predictions. There we go. I think that's good. We could also specify what kind of optimizations we want to apply during the gradient descent. Oh, Drawing Brothers. So how do we start that kind of a project? Can we firstly implement a regression model like linear regression? Yep. Mm-hmm. Since this is the basic algorithm. You're right. So here's the thing. If everyone listening right now, you've all been tricked. I'm telling you right now, you've been tricked, unless you already know what the trick is. But there's a difference between like machine learning with different types of regression models, like linear regression learning. Doesn't that sound like, oh, it's really complex and advanced and powerful, deep machine learning? It seems like it's that much better. But you know what? Here's the difference. I'm going to show you on the screen if you can see it. Let's actually do a quick look. You know what? Let's get Jules started. We'll get Jules started really quick. And then we will, we'll draw you what the difference is. Here we go. All right, Jules, create the plan. Here we go. And then we're going to show you what the difference is between standard machine learning and deep learning. Here it goes. Jules is off to the races. So this is kind of neat. Just kind of taking a look back here before we start. We'll draw some information here in a second. We'll do some drawing. But right now, take a look at this. Whoa, check it out. Oh, it already got started. Okay. Here we go. Let's read through this. Let's see what it has. Create a project structure. I'll create a lib.rs file, house the core framework components. Lib.rs will have modules for layers, activations, and the model itself. I'll also move boilerplate main function from the main RS run into a run function in librs. Okay. Implement activation functions. I'll create the activation. It also need those for backpropagation. Implement layers. I'll create layers modules. This will contain the layer, trait, a dense layer implementation, which is your standard layer, which is just basically matrix. That's all it is. It's just a matrix, like a 10 by 10 matrix, for example, is dense layer. It handles the weights and bias. Oh, and it also has a separate matrix for the bias, which is a one-dimensional array on the so you've got a two-dimensional array with the weights, so it's like a 10 by 10. And then you have a one-dimensional array with maybe 10 elements deep. So the 10 by 10 will be 100 elements in the weights, and the biases will be 10 elements. And that's used to offset any of the positions of the output from the coefficients. There's a whole bunch of like math words in there, but you don't have to worry about it because really you're just doing array math. It's just array math. Tommy Grizzo, this is good stuff. Thank you. Appreciate it. This is we're walking through artificial intelligence, the beginnings, the things that you need to know in order to write your own machine learning framework from scratch. This is really exciting. I like it. We're also going to use Google Jules for the first time to at least get us started to see what it comes up with. So it's going to implement the model, create a model module with a sequential model. Oh, so it's going to stack the layers. Building a model right now. I'm going to look on. Excellent, very cool. Let's see here. So let's see. Let me double check here really quick. So Sirajan, any projects in Rust? Yeah, I definitely. It might be kind of interesting to get some machine learning going with Rust, like we're doing right now. I think there'd be some interesting projects there. But you can build something with WASM, right? WASM. Yeah. Or well, the subtitles are going to have trouble with that. But WebAssembly is what it is. WebAssembly, and you can compile Rust to run in the browser to do something. So you might be able to do something like you can do some extra advanced training there. That actually works really nicely. Games and game engines in Rust, so that's kind of neat. You can have an AI do that. I wonder if ETH allows you to use AI agents during your coding session. It probably does, I'm guessing, because it's the modern approach now, right? It's a 3D mesh, right? It's a multi-layered 3D mesh that represents the coefficients that go into creating a probabilistic output and it's not really AI, but it works pretty good though, doesn't it? It does a pretty good job, I say. It's just probability. It feels like intelligence. It does feel like it is. And let's think about the human brain really quick. Okay, so the human brain has a similar structure to what we're like representing in AI, right? You've got all these like neurons and synapses, and there's an array of them. Like what is it? 100 billion? Is it? I think it's 100 billion of them in your brain. And you can kind of think of each of them as data points for data storage, but also at the same time, they can be used as a feed-forward neural network. So they're coefficients and they're data storage, and there's activations as well, which helps you perceive the world in a way. Yeah, WASM, heard of it? Cool. WebAssembly will surely make use of it. It's really powerful because you can build really build games in the browsers more efficiently, like a Rust engine. So let's take a peek here. Let's see what it's doing. Jules it's off to the races. Like it's just going. It's taken over everything here. I'm just kind of curious, and it will verify and complete to ensure the XOR example trains correctly and produces the expected output. Okay. Cool. So it's going. LSR Rust framework. Okay. It's created the project structure. It's done a lot of things already. While we've been talking, it's just been working away here for us. This is kind of neat. Right. It's got the losses. So it's doing mean squared error. Okay. So MSE, it's going to do mean squared error for its loss function that is used as the calculation when you ask a model a question. It will give you an answer, and the answer will be wrong. And so you can use MSE to see how wrong it is. And then you take that delta and multiply it by a fraction, which is the learning rate. And then you apply through back propagation the changes of the that need to go into the coefficients of the parameters of the model. We're using Jules today. Google Jules. If you've never heard of it, it's an AI agent that runs in the web browser and it does your work for you. Surprised that they've had this for 2 years already, and it probably been longer. They probably had this for long. Google probably had this for longer, and they just didn't release it. Is this vibe coding? It is, because I'm not doing anything right now. Oh, sweet. It's ready for review. Check it out. It looks like it might be done already. It might already be done. It took 8 minutes. Google Jules says it took 8 minutes. Let's see. What are my options here? Publish branch, publish PR, publish a branch, and generate PR. Publish branch. Yes, let's do both. Publish PR. Here we go. Wow, is this free? Yeah, I think so. So Jules is free. It gives you so many credits, and then you would pay, right? You'd have to pay for it, I think. So I've got a plan that gives me some credits that I can use, but it's a try then buy pricing model, right? Try then. Created the pull request. All right, let's check out. Let's see what it did, you guys. All right. Is it Claude Code? This is Jules. This is Google Jules. Check it out. It actually did all the stuff for us already. So Google Jules is like Claude Code. It's exactly like code. What's the name of this project? Okay. Another day, another project. You got it. So what we did was we're doing Rust artificial intelligence. We're going to do a Rust deep learning framework. We used Google Jules for the first time because we wanted to try it out. Okay, so let's get back to what Jules did for us. So Jules created a pull request, and it says it's done. Actually, let's check it out. Let's see what the pull request looks like. Here we go. We're going to reload the page, and we got a pull request. Look at there. All right, Jules. What did Jules do? What did Google Jules do? All right. Create a simple deep learning framework in Rust with an XOR example. All right. We're going to review the code now. We're going to read it. Here we go. So let's get back to see what did Google do? This change implements a simple deep learning framework in Rust from scratch. The framework includes the following components: a matrix, an abstraction. This is what I wanted to do. It's similar to ND array that you would see in NumPy, right? In NumPy, you have an ND array, which is just an array object that has some nice built-ins. You have a dense layer for fully connected networks, which just means it's a multidimensional array. That's all that means. You've got sigmoid, tanh, and ReLU activation functions, which is just these functions they prevent explosions of numbers to go big, because they always, no matter how big of a number you put into the function, like the sigmoid function and tanh function, it always returns 1, 0, or -1, basically, except for ReLU. ReLU does a little bit different. Mean squared error for the loss function, which is used to calculate the error output. Sign up for API keys, and then you get your own sandbox, your own dedicated sandbox. Otherwise, you could just use the demo keys, but then everyone has access to that data, so you got to be careful. All right, here, let's go back to Jules again. All right, so mean squared error for the loss function, standard gradient descent optimizer for training, a sequential model for stacking layers. Oh, cool. Okay. This is actually what we're looking for. Let's see. And then it has Jules reporting for duty. I'm here to lend hand when you're ready to start a review. Oh, no way. It can do its own review. Wait a second. It can. All right. We have to try that out. You guys, we have to try that out. We have to see. Let's have it review. Let's have it review PR1. We'll have it review pull request 1. Okay. Here we go. Okay. Review the code in PR number 1. Let's see what it does. You guys. I'm actually kind of curious to see what it'll do. It's going to review its own code. We're playing with Jules today. Google Jules. If you never heard about it, it's an AI coding agent, and it's been out longer than all the other ones. And it's just kind of crazy that Claude Code got popular, Codex got popular, and there's Gemini now, which is a CLI. But Jules has been out for longer than that. I'm just surprised that we haven't been using it as much. So we're giving it a shot today. We're seeing how it goes. And it's done a good job. Actually, I haven't read the code myself. While it's making its own code review, let's see. Let's see if we can, let's read the code itself. Let's see what it came out with. All right, so we've got our cargo TOML activations. Oh, sweet. It implements it. Oh, look at that. It's got It's mapping over the elements and then activating each of the parameters in the array. Is it so? It's one of the first AI coding engines. It seems like it. It does, because when I was signing up, I saw that their GitHub OAuth key, their GitHub OAuth key was created 2 years ago. It was created more than 2 years ago, which tells you what they were planning all along. These goals. So I'm actually kind of surprised that it's not more popular because of how far it's come. Okay, so it implemented the derivative. You guys, it implemented the derivative. Yes. All right, we didn't even have to explain it. Isn't that crazy? Sir, your maths must be strong. Where did you learn the probabilistic maths or the maths that's needed for AI machine learning? YouTube. Isn't that crazy? I learned on YouTube. So we've got tan H, we got sigmoid, and the derivative for tan H. Yep, here we go. Looks good to me. Okay, and then we've got ReLU. Check it out. Yep, here it is. Isn't this cool? Oh, that looks awesome. The code is so clean and simple. You know what, you guys? It's actually almost how I would write the code. I would almost write the code this way. It's how good it is. This is impressive. This is really impressive. Okay. Oh, is epsilon? It has epsilon in here? Wait, what is the E is, for me, the letter E is like an epsilon. But it looks like it's something different in Rust in this case. It says constant. It says it's a constant, E dot power F. Okay, so maybe this is something you can do in Rust, like in JavaScript and Java and world applications when you're writing your first machine learning framework. MNIST dataset, which is a bunch of handwritten, hand-drawn numbers. That's a great way to learn how to build machine learning and with this data set, because it does a pretty good job. It's nice to have data because you need data to train the AI model. But I like something even simpler. I like the XOR operator to be trained because it's a nonlinear operator that can't be trained through normal linear regression. The XOR operator requires deep learning. I like to use that as my hello world because it's just simple and it doesn't require any data, because you can synthesize the data and you know what the output is. It's deterministic. Mamlok, hello, I'm new here. What's the topic? All right, so here's the topic. We're doing Rust deep learning. So we've got Rust deep learning, and we're also at the same time, we're using Jules, which is Google's online coding agent that has been out for more than 2 years. Isn't that crazy? It's basically one of the first coding agents that no one's ever used. I mean, I hear no one talking about Jules. So I wanted to try it. And you know what? It's doing a really good job, like an amazing job. So that's what we're doing. Rust with reinforcements will be the best thing. I think so. Yeah, Jam Buster. It's going to be amazing because you're going to get powerful performance of the language itself. And you'll also get, the extra safeties built into the compiler. It's going to be really powerful. And so we've got a long running plan with this. We have a lot of plans. So we're not going to end it. We're not going to end just on this. We're going to walk through the code. Here's what we're doing. We're not done today yet. We want to walk through the code that the AI wrote. We're going to see what it wrote. And then we're going to try it out. We're going to run it and see how good it does. Then I want to make some updates and edits to make it more of my own, because I have different design patterns that I might want to implement using operator overloads, because I think that was a little bit nicer in Rust, which you can do it in Rust. You can also do it in Python. There's other languages that you can, like the multiplication symbol, you can multiply two objects together, which would be like a multidimensional array. And that gives you, so you can do outer product where you're multiplying the matmult, the matrices, you're multiplying. Check this out. We need to learn. We're doing a learning session. Standard machine learning. And we're going to compare that to, actually, let's get this here. Standard machine learning. And then we'll go over here and we'll say deep machine learning. All right. We're going to do deep machine learning. All right. There seems like there's some big differences, doesn't there? Doesn't it seem like there's going to be some giant differences between these two things? One is deep. That means it goes further, right? Doesn't it seem like it feels like that? So here's an array. And then inside the array, you have a bunch of weights. So we just basically in every weight is a floating point number. So this is all that means. It's just a floating point number. So you've got a bunch of floating point numbers here. And this is, we'll keep it simple. We'll just make it a one-dimensional array because you can do that with machine learning. It's pretty simple. And we'll call it like this, like a number like number 1 and number 2, number -1, 0.07, right? They're actual numbers. So let's actually write those in because I think it's helpful to see. We'll just do this. We'll say like 1, and then we'll go over here and we'll say 2. And then we'll go on this one and we'll say 0.1. We'll say 0. And then we'll delete this. Parameters. If you heard like 7 billion parameters or this model has 1 trillion parameters, they're numbers, right? These are numbers, including the weights, which are the coefficients that go into the equation of just multiplying when you're multiplying the matrix C to the other. They're just numbers. That's all they are, numbers. They're floating point numbers. And so you've got your numbers, and it's the same for machine learning. So you've got your input layer, and then you've got your knowledge layer or just extra parameters layer, and then you've got your output layer. So you're probably already ahead here. You probably already know what's happening. So you've got the input, right? And then what you do is you've got your input, you've got your hidden, although this hidden layer, and then you've got your output layer, which translates to the output, which you use an inner dot product to create the result, which you answer. And so we have here, let's go a little bit further. So here we go. Here's our standard machine learning. And then when you want to use this model or train this model, you want to give it its input. And the input is going to be numbers, right? All of this is numbers, but it's all represented as numbers, whether it's a picture, an image, a video, text, user input, photo sensors, like other like heat sensors, anything has to be a number. So you just can convert it to a number. It all is easy to convert to a number. It's really simple. And so you've got your input layer here, and we'll just say like it'll be like the number 7, for example. And then you do a map mult on that, right? You multiply each of these map mult. Just multiply the numbers, and then right, and then it creates a matrix, and you're doing basically it's 7, and the coefficients are 1, 0, and 2. You multiply those, and then it gives you another array, and then you do the same thing with the output of that array to this next array. So we'll just kind of like make it a little bit easier here. We'll just visualize this a little bit better. And then once we did this, I'll show you what deep learning looks like. You'll be like, hold on a second. That's what deep learning is? And you'll feel like you've been cheated this whole time because it sounds like it's really advanced. And so you do the same thing here with this, and you just multiply, and then you do the same thing again, and you multiply. And then you get this output, which is, it's going to represent some other number. It doesn't matter what the numbers are because you can train the model to be anything on the input. You can train it to be whatever you want on the output. So it could be a binary classification model where it says you want the output to be, if it's an odd number, then the answer is 1. If it's an even number, the answer is 0. And then you can have the model learn that odd numbers and even numbers. Isn't that cool? And then you can pass in these numbers, and then it will know to identify an odd and an even number. And you've just trained your own machine learning model that understands how to identify any number as odd or even. Isn't that cool? So yeah, that'll be like odd or even. Odd or even. Something like that. Yeah. So that'll be like the output. And check this out. So that's standard machine learning. All right. So we got that. We understand what that looks like, right? So we got standard machine learning here. And then here's deep learning. Are you guys ready? You guys ready for deep learning? Are you ready for deep learning? Is it gonna be that much more complex? I don't know. I think you already know what's gonna happen here. I'm pretty sure you know what's gonna happen. Here's what we're gonna do. We're gonna take this and we're gonna copy and paste that. And now we're gonna put some arrows in. And here we go, you guys. Check this out. Arrow. One more arrow. Here we go. Boom. That's it. Do you see what the difference is between the two? Do you see what the difference is between deep machine learning and standard machine learning? They just added another matrix. They just added another layer. Isn't that crazy? You also, up to what extent can I fine-tune a 4-bit model after quantization? I'm trying to do that for the 5.4 mini. Oh, you can, you totally can. It'll totally work. You just need to make sure, because the 4 bits isn't a lot for a floating point number. So if you're going to fine-tune that, you might, and you want to keep it in 4 bits, then you just want to make sure that your hyperparameter, your training, your learning rate needs to be high enough. Because if it's too small, then it won't be able to store the deltas, and it just won't work because you'll have overflow. So you got to be careful on 4-bit when you're doing fine tuning. So just make sure you have a high enough learning rate. You'll have to figure out what it's going to be. I don't know what it's going to be, but with the 4-bit weights, that's not a lot. So, because floating points can be like, you can train an 16-bit or even 32-bit or even 64-bit, right? So give it a lot of bits if you want. But here you go, you guys. Deep learning versus standard learning. This whole time you never knew, and you can just keep adding more layers. And so now you have got a question. Well, how big are these LLMs? The LLMs, the large language models. How many? Because they're deep learning, right? How many layers are they? Well, it turns out there's quite a few, but I'll just give you the answer. It's, I believe GPT-3 or GPT-4 was something like around 92 layers. So 92 of these hidden layers. But there's more than just 3 parameters in them. There are like billions of parameters, so like a lot, right? There are a ton of. Learning is a reinforcement learning algorithm that trains an agent to assign values to its possible actions based on its current state without requiring a model of the environment. Model free. It can handle problems such as stochastic, random, transitions, and rewards without requiring adaptation. Input, like a photograph, a picture of an apple. It's a mango, right? Okay, so the model got it wrong. So the output was, it's a mango. The model got it wrong. Okay, so wrong, it's an apple. Here's the feedback, which you use your delta. So you want to do a loss function. You can do a lot of different varieties of loss functions. So MSE is a common simple one, mean squared error. Learning is a popular model-free reinforcement learning algorithm that helps an agent to learn. It helps an agent learn how to make best decisions by interacting with its environment. Instead of needing a model of the environment, the agent learns purely from experience by trying different actions. Imagine this, okay, Jambuster. I work on a project where we first create SLM, I think standard learning model, or what is SLM model? Let's see here. For each of the things like behavior, talking, or thinking. Then we connect all of the SLM models in one giant brain type of cell. AI and machine learning. I'm doing really good. We used Google Jules to write for us a AI framework in Rust just from scratch. And I'm comparing to see how I would write it. And it did a really good job. And it wrote minimal code. Look, it actually did a really good job. I think it only wrote like a couple hundred lines of code. It's so clean. It's super clean. It's just very satisfying to see. Take existing models and then freeze certain layers so that the layers in the middle stay the same. And you can add layers on the input to output to change and add more knowledge without having to run through the whole model. You can freeze the middle layers. So then when you're doing back propagation, that gives you the ability to only have to update maybe the input and output or 2 extra layers. There's lots of approaches. There's just a ton of different options that you can do to optimize existing training models, pre-trained models, and then applying your own needs to it. So it's actually, there's a lot of cool ideas in there. And through artificial intelligence, we're doing the basics. Your AI is open source, right? Yeah, it's open source. So I'll paste it. This is here. So Google Jules wrote it, but it's not here. I'm going to paste it to you in chat so you guys have it again. Here we go. Here's the link. So you can have that link. Boom. There's the link. Are they free or paid? Completely open source, completely free. Google Jules is not open source though, but it is free. There's a free option. I'm currently using free. I've used 13 minutes and it's still working. So it's going fine. We had the AI write the code, and then evaluate its code. So it's got an array of floating point numbers. F64, you guys, look at, we're in the big, so we were talking about, earlier we were talking about 4-bit weights. Look at these weights, 64 bits, you guys. These are really big, 64 bits per parameter. Isn't that crazy? Okay, so we've got a forward and a backward. So we can do, that allows us to do back propagation for applying our gradients when we're in the training model. And then we got forward when we're doing predictions. And that works for the ReLU, for the tanh, and for the sigmoid, which is great. Okay, here's our layers. So we've got a layer, and then the layer's got forward, backward, and get output, which is interesting. I would kind of think that the get output would be available here, right? It seems like that's where you would get it, but it looks like it's got it might be a helper function, some sort of helper function. Why Rust? Baldwin 4, official. This is the official Baldwin 4, you guys. Official Baldwin 4 says, why Rust? Because it's super fast, it's clean, it's got a really powerful compiler, and it's got the ability to give us some powerful concurrency safety capabilities that we can use for training. We can accelerate our training across multiple GPUs at the same time, for example. And we'll do that in the future. So I want to write our own kernels, our own GPU kernels that will give us the ability to write mega kernels to implement matmul and activations all in one. So a fused kernel. We tried to train SLM with specific things, only like talking or thinking. Interesting. Okay. You mean one SLM model for talking, one SLM model for thinking base, the word meaning, and then we tried to connect all those things. That sounds interesting. Your results. I'm very curious about Jambuster. I'm curious about your results. That's really cool. Do you know about OnXX models? JB. Let's see. Let's check out OnXX really quick. OnXX. What is this? OnXX. Let's check out. I'm really curious about what is OnXX. Oh, that is a stock ticker, but it's also Open Neural Network Exchange. Wait, hold on. There are multiple. Yes. Okay. Here we go. Let's learn here. Open Neural Network Exchange is an open source format, machine learning. Oh, models. Okay. So it's a format for storing the weights and the models, probably like onto disk in a file format, which totally makes sense because it goes more a machine in one model. Can you give me any ideas about this because you are a pro-ish? Like pro-ish. I've been working. Unity supports Onyx. Oh, cool. Does it? Okay. So in machine learning models, Jambuster, I'll think about this real quick. I need to think about what you're describing because I'm really curious about your findings and your results when you've connected the two together. I think there's a lot of power. I think you can get a lot out of it. You might need like a third model in there to interpret the vision. So like your brain, you've got one model that does vision, you've got another model that does hearing, and you've got a master central control that interprets everything together. MCP server, or what are we doing? We're talking about artificial intelligence. We were talking about MCP earlier with the PubNub MCP, and you can easily grab that and install it into any of your coding agents. And now we're looking at let's see, what is it? Onyx. Yeah, the Onyx format. Keepers enable interoperability and portability, which makes it easy. It needs to know how to use those numbers in a matrix. When the activations, what does the input look like? Are there is there a transformer? What kind of attention layers do we have? Is it a CNN? Are we using filters, multiple filters in array for a CNN? There's just a lot that goes into it, right? So having it all in one file is really cool. That's really cool. Another account. Hey, I've built my own deep learning framework from scratch. Nice. That's what we're doing today. And called it Cobra. And it is hard and not scalable until I researched more about that, until I implemented my own linear algebra backend with AutoDiff. That sounds really powerful. So another account, how far did you go? Did you do like a distributed compute training model where it can distribute the workload across multiple machines? Did you do it or from a concurrent perspective where you're using multiple hardware components on the box, like multiple CPUs or multiple GPUs? There's a lot of options in there. Your building sounds really powerful. So you tried to train an SLM with specific things like just talking or thinking, and then you merged them. I think you need to create a third model that can interpret the results of those other two models. Like you've got a thinking model, you've got a vision model, you've got a like a word model or a talking model. I think you have to have something that unifies everything together. Just walked through the code on Jules, and let's see, it gave us a review. So let's take a look at what's ready for review. Refactor improved deep learning framework design. Let's see here. I tested the refactored code and verified it compiles. Let's see. Oh, so it did do some verification. I'm actually kind of, let's just check to see what it looked. Okay, here's what it did. I have reviewed the code. It didn't post it to GitHub, which is why I was confused. So suggestions for improvements. The sequential model is currently a vec dense, which limits the model to only dense layers. Oh, we can do a vec box dyn layer to allow different types of layers in the future. Interesting. That is kind of neat. So it allows you to do different kinds of layers, and then, but also maintain concurrency safety. Activations. The sigmoid and tanh structs with the backward method recomputes the forward pass. Oh, during the back pass, it has to recompute the forward pass. That's a problem. It needs to store the, that's nice to use DL framework for small model training. Yes, it is. Even for, PyTorch, during development, you faced another fact that it's CPU based, so you need to move to GPU and implementing literally everything that is almost like Torch, but with Python, Cuppy, and NumPy instead of C++. Yeah, you're going to run into some bottlenecks there, another account. You need to be able to access the GPU in a way that is efficient, because submitting work to the GPU is probably the slowest part of the communication of the AI training. You want to be able to submit work to the GPU, have the GPU run all of its cores on enough work, and then provide feedback back to the user space application that's running on your OS. And then you will know what to do next. So it's possible that you'll run into some bottlenecks by doing that. You got to be you'll have to be careful. But guess what? If you just do, this is actually really cool, another account. If you just do matrix multiplications and that's it, and that's all you do, so you instantiate texture memory with all of your floating point values, which are your weights, the parameters of the model, the coefficients of the equation, you take those and you put those as texture memory. And then you create a kernel in the GPU or shader that can multiply all those together, a matmult. And then you can do a simple 2x2 or 3-dimensional matmult. And that will give you an output. And then you can take that data and then you can do, you can run a loss on it back at the CPU layer. And then you can do back propagation. And then you resubmit the work and do more matmult. So if you just do all your matmults, even if it's just matmult and every single matmult is being submitted to the GPU, then you will get an acceleration. And it's fine, even if you're doing a lot, because matmults, but the matmults need to be pretty big. If it's just like a few hundred, you're not going to get much of an acceleration. You need something that's at least a couple hundred kilobytes worth before you'll start seeing acceleration. Is this like a Google Vertex or whatever? The stack is just Rust. Or I guess if we were talking about what we're implementing here on the screen, in this chat here today, texture memory, doesn't texture memory support higher dimension textures? Yeah, so there's multiple there's multiple ways, multiple options. You can have multi-dimensional textures in the primitives that you can perform work on, which parallelize even more cleanly. So you'll have to look. CUDA, actually that's a really good idea. So you've got Python, and then you can use CUDA if you've got an NVIDIA supported hardware on your system. If you've got an NVIDIA supported hardware, you can use CUDA with your Python, and it's actually pretty easy. And CUDA also, just a couple of years ago, came out with a really nice way to write your own GPU kernels. Really clean way to write your own GPU kernels. How are these CUDA cores help with the workload? The CUDA cores, okay, so the CUDA core is going to be, just it's a simple like version of a CPU. It does like just basic math, but it does basic math really well, like multiplication. Multiplication and division are one of the most computationally intensive tasks or operations in a compute layer. So by using CUDA cores and having like 1,000 or 10,000 of them, you can do a lot of multiplications all at once at the same time. And then you can get, that's how Bitcoin hashes are working as well. It's doing a lot of randomization to compute a hash in parallel. And that's why GPUs are used for like Bitcoin mining. You can do that same policy with a matrix multiplication, which is the primary way machine learning models work. Recent ton of LLM based stuff, which I'm really inclined to go through. So what's your long-term vision for this channel? Long-term vision for this channel here on YouTube, we'll be going through just a lot of technology. Software engineering focused. We'll be talking about software engineering, algorithms, distributed algorithms, machine learning, AI focus as well, because there's a lot to learn there. And then using frameworks, trying out different systems, like we're using Google Jules today. We'll be trying that out. CUDA requires a minimum of 32 threads per task. Oh, does it? I didn't know that. I didn't know CUDA had a requirement. That's actually kind of interesting. Well, you're clearly using GitHub too. So the stack would be Rust, GIF. Oh yeah, thank you, Baldwin. Thank you. You bring a good point. You bring a really good point. GitHub is part of the stack. I didn't consider that. That's what I'm asking. How does this help me make a small model for a specific use case? So you can actually, if you're very interested, you could do this to make your own small model, and it will work very well, like very well. And you won't necessarily need GPU compute, GPU acceleration. You won't necessarily need changes, and then we'll merge it, and then we'll have our own open source Rust-based machine learning framework that works really well. And I'll repaste this into the chat. And what we could do is I can show you guys how to use this framework to train anything. You can train it to do anything you want, which is really amazing. You can even use an existing larger model, like a large language model, to create training data to distill this model into any kind of extremely efficient model. So what you can do with this is it allows you to run it like you could run it on your phone because it's that small. You can run it on an embedded device because it will be small enough to do that. And that's why you want to write your own framework. And that's like a really good reason to do it. A really good reason for the transformer on the CPU with smaller model size. It did so fast, actually faster than it did on the same size on a GPU. Yeah, because the submitting work to the GPU, especially with an LLM, the majority of the latency can actually just be in submitting the work itself. But if you have a small enough model, keeping it on the CPU means that it could be even faster. Isn't that amazing? It can go way faster. It's actually cool, isn't it? You can scale up the model size and it almost never works on the CPU. Yeah. See, that's when you need something like a hardware accelerator, like a TPU, a tensor processing unit, or a GPU to accelerate that. And you need it to do matrix multiplications and activations. If you can do that all in one go in a forward pass, and you can even do multiple layers all in one, you can do like a 3D by 3D matrix multiplication, which I'm really surprised that a lot of people are doing. You should be doing that because that's like a bump up in, maybe OpenAI is doing that and they're not telling us. You never know. Why not use TensorFlow? Flow Lite. Oh yeah, TensorFlow Lite. You could totally use TensorFlow Lite. TensorFlow Lite is like a light. I'm not sure if it has GPU acceleration, but it might be CPU, and it will. It runs TensorFlow models, but it lets you run it on less capable devices. So that's a really good idea, TensorFlow Lite. But then you need to use TensorFlow. Keras, make sure to use Keras when I recommend that. It's an easier to use API. We're using CNNs, but they migrated to vision transformers, which is the current way, a modern approach, similar to large language models, how they use the transformer approach for, self-attention. They're doing that within the AI taxis now. they're doing that there too. That's vision transformers is what you want. CNNs can still work and they're efficient and they do the job and they can still serve a purpose. But if you're wanting to be on the bleeding edge, you want to use vision transformers. Another account, but only runs good on GPU with the same or slower than CPU speed, but at least it runs. Yeah, you're totally right. It'll go. You can make it go in any of these cases. Yep, TensorFlow, Keras, and AutoML. Yeah, I forgot about AutoML. AutoML is great because you can you don't have to worry about the hyperparameters. Because when you're doing it yourself, like you can see here, we're building our own framework, but now we're going to have to figure out the hyperparameters. We're like, how many batches do we want to do during training? What does our SGD look like? How are we going to shuffle the data? How are we going to parse out different segments of the data for testing? What is our learning rate? What kind of activations do we want to use? How dense do we want each of our layers? But Baldwin, thank you. You just saved the day. AutoML helps take care of all those decisions for you. So also check out AutoML. So cool with emoji sunglasses. We'll get the code. We'll run it next time, which will be tomorrow. Okay, so Jules just connects to GitHub, right? Yep, that's what it did. So we got Jules here. We asked to do some tasks. I just submitted the refactored code. Would you please specify what changes, like all? So all. So I'm going to have it finish its work and then contribute the changes to this branch. And then we'll walk through the code next time. We'll see what it did. And then we'll run it on... it probably won't... I need to spin up a server to run it because it's going to compile and it will freeze my video. Because my video and running video streaming on the same box at the same time will be live tomorrow, and we'll be going through this Rust code that the AI wrote for us, and we'll be making changes for ourselves. We'll run it ourselves. We'll see how it works, and then we'll see how to use it. We'll show you how to use basically your own self-written deep learning machine learning model, and we'll show you how you can basically train it to do anything you want, which is really exciting. Yeah.